Hello, so let's start today's topic with a problem on the complex Fourier transform, or simply the Fourier transform. And to begin with, I must remember you that the complex Fourier transform of a function fx, where x lies between minus infinity to plus infinity, is defined as f of n that equals to integral minus infinity to plus infinity capital F of x e to the power I nx dx, where n is a positive integer. Now here the term e to the power I nx, as I have told in my last class, that it is known as the kernel of the transformation. So e to the power I nx, this part is known as the kernel, K-E-R-N-E-L, kernel of the transformation. Now let's do a sum on this. Say we have a problem that find the Fourier transformation of f of x. F of x should be given, and f of x equals to 1 minus x square, where mod of x less than 1 and the value is 0, where mod of x is greater than 1. So let's do this sum. We have to use the Fourier transformation and find out the transformation value of f of x. Now, as in the formula given above, we can see that here the limit has been changed, or we can write it from minus infinity to plus infinity as well. But as the function is defined here as 1 minus x square, the value of the function is 1 minus x square, where mod x is less than 1. That means that within the limit minus 1 to plus 1, within the limit minus 1 to plus 1, that is the function is defined as mod x. Say this is plus 1 and this is minus 1, and the function is defined as mod of x is less than 1. That is within minus 1 to plus 1, this entire part, in this entire region, the value of the function is 1 minus x square, and beyond the value of plus 1 or minus 1, that is when mod x is greater than 1, that is when mod x, or rather x is greater than plus 1 or x is greater than minus 1, the function 0, the function vanishes. So that's why we can write this integral, the integral as minus infinity to plus infinity, or rather we can reduce this integral from, and we can reduce this range of this integration and write it as minus 1 to plus 1, since beyond the range minus 1 to plus 1, the value of the function is 0 elsewhere. So we have f of n equals to integral minus 1 to plus 1. So that is the range in which the function is defined as 1 minus x square. The value of the function is 1 minus x square. So this is f of x. And then e to the power I nx dx. So this is e to the power I nx dx. As I have told in my last lecture, that is in lecture number 1 of Fourier transform, that you can find this integral in many books. It is written as e to the power minus of I nx dx. Nothing is wrong. You can write it as e to the power minus I nx dx, or you can write it as e to the power I nx. Okay. Later on, I will show you that whether e to the power minus I nx is right or wrong. Later on, I will show you also. So now we have to perform the integration from this step. So as we can see that we can perform this integration by using integration by parts. So keeping 1 minus x square as the first function, as because the other function is an exponential one, so e to the power I in x should be our second function. So by applying integration by parts, we can write it as the first function into integral of the second, that is e to the power I in x divided by I n, where the limit should be minus infinity, minus 1 to plus 1, and then minus integral minus 1 to plus 1, differentiation of the first, that is minus of 2x, into integral of the second, that is e to the power I n x by I n into dx. Okay. Now here the limit is plus 1 and minus 1. So by putting the limits here, we can find that 1 minus of plus 1 square, that is 1 minus 1, makes it 0. And if the lower limit is put here, that is x square, minus 1 square means again plus 1. So by putting these limits of plus 1 and minus 1, this first part vanishes. So I can skip this part in my next step, and I can write it as f of n equals to so it will be minus minus plus, that is twice integral, or rather 2 by I n 2 by I n x into e to the power I n x dx. Here also the integral limit is minus 1 to plus 1. So the integration reduces somewhat and it becomes 2 by I n integral minus 1 to plus 1 e to the power x into e to the power I n x dx. Okay, so the first part reduces here. Now again proceeding and following the integration by parts here. So it will be 2 by I n, and then the first function, that is x, into integral of the second, that is e to the power I n x by I n. The limit is minus 1 plus 1, then minus differential of the integral minus 1 to plus 1, differential of the first, that is 1, integral of the second, that is e to the power I n x by I n into dx. Is it okay? Last part, denominator e in e, last part denominator. Last part denominator means Manwarul, what are you saying? Last part denominator e in hobe. Here I can get you Is it okay till now? partial integration. This part I have kept that 2 by in I have kept this 2 by in common and then proceeding only the integral part here. So what I get, so it will be 2 by I square n square, that is minus of n square, then x, that is e to the power in minus of e to the power minus in, e to the power in minus of, and since this is here minus 1 also, so it will be e to the power in plus e to the power minus in. Is it okay? E to the power in plus e to the power minus in, and if I think I can multiply and then it will be easier for you. Now this term here, it will be minus again 2 by I square n square, that is minus of n square. Or we can write it as plus. So it will be plus 2 by n square integral e to the power I nx dx, and this will give me e to the power I nx, e to the power I nx by I n, where the limit is again minus 1 to plus 1. Is it okay? So we have minus 2 by n square e to the power I n plus e to the power of minus I n plus 2 by I n cube, and then e to the power I n minus e to the power minus of I n, minus e to the power minus of I n. Now e to the power ix plus e to the power minus ix, what we get? E to the power ix, e to the power in means cos n plus I sin n, e to the power in means cos n plus I sin n, and then e to the power minus in means cos n minus of I sin n. So e to the power in plus e to the power minus of in will give us 2 cos n. So it will be minus 4 by n square cos n. Is it okay? Minus 4 by n square cos n, and then plus 2 by I n cube, and e to the power I n minus of e to the power minus I n, that means cos n terms cancels, and we have twice I sin n, and that I should cancels, twice I sin n, and that I should cancels. So we have minus 4 by n square cos n plus 4 by n cube sin n. Is it okay? So if we take, to get the answer, if we take minus 4 by n cube common, then we have n cos n, then we have n cos n minus of sin n. So you can write the answer in this way also, that is minus 4 by n cube into n cos n minus of sin n. So this is the Fourier complex transform, or just the Fourier transform of the function f of x equals to 1 minus x square, where x is limited between minus 1 to plus 1, or the limit gives us as mod of x less than 1, and the value of the function is 0, where mod of x greater than 1. Manwar will just go through the solution and you will find it okay. I think everybody finds this solution okay. So just go through the problem once more and you will find it okay. Is it okay? Arindam, Shushmita, Uday, Moumita, have you any queries? Is it okay? Okay. Then let's move on to another problem and find its Fourier transform. So the next problem is find the Fourier transform of fx. Find the Fourier transform of fx, which is given as 1 when mod of x less than a, and then 0 when mod of x greater than a. So this is the function given. This is the function given. Again, you can find that as the function tells us that this is say plus a and this is minus a, and that mod of x less than 1. When mod of x less than 1, it means that when x less than a, again when x less than minus of a. Okay, so this is the entire range. This is the range where the functional value is 1. Okay, and then mod of x greater than a means that where the value x is greater than plus a or x is greater than minus a, that is the range, or that is the region in which the function itself is 0. So we can write this integral as f of n. So the Fourier transformation, that is f of n, it can be written as the integral, the range is somewhat changed, and it changes to minus a to plus a, and then the functional value of fx is 1 here, e to the power into e to the power I nx dx. So this is the range of the integration, and the integration range changes accordingly. Now this means that the value of the integration, it is e to the power I nx by I n, and then the limit minus a to plus a, so 1 by in, and then e to the power in a minus e to the power minus of in a, and this will give us twice I sin n a, twice I sin n a divided by in, so it will be 2 by n into sin n a. Is it okay? Now let's try the other formula given, that is, if we use e to the power minus of I in x dx, what will happen? That is, if the Fourier transform, if the formula of the Fourier transform is written as capital or rather f of n equals to integral minus infinity to plus infinity f of x e to the power minus I in x dx. Okay. So you can use either of these formulas as you wish. So now let's move on to derive another transformation, or find out another transformation. So now we are going to finding the transformation of e to the power minus at into ut. So now there is a product of two functions, and the new function is e to the power minus at into ut. So find the transformation f of x equals to e to the power minus at into ut. As you can see, now the function is given in time domain. Now the function is given in time domain, and the function looks like, if you plot this function, the function looks like this. So this is the time domain form. If the function is written as, don't write it as f of x, write it as gt or f of t. So if the function gt, here the value is 1, and then as time increases, the value of the function decreases exponentially, as because the term e to the power minus of at. Now, if the function is written as gt, if the function is written or if the function is given in time domain, that is gt, then we can write it as the Fourier transform as g omega. So here I have applied the transformation, and the transformation actually converts the function from its time domain to its frequency domain, and that is why I have written it as capital G of omega. Capital G of omega. If the function is given as f of t, we have to write it as capital F of omega. So let's take the function as gt, and that's why the transformation is g omega. Now g omega should be equals to, as by the definition, minus infinity to plus infinity, then the function gt, that is e to the power minus at ut, and then e to the power minus of j omega t dt. Is it okay? So here, as you can see, that I have using the different form of the kernel as e to the power minus of I omega t, or e to the power minus of j omega t, as j is the complex quantity, complex number. So here this way you can also represent the Fourier transformation, or you can also calculate the Fourier transformation. Okay. Now because here from the definition we can write it as minus infinity, integral minus infinity to plus infinity, but as the function given here, and if this is its functional form, this is the functional form, and as you can see that the value is actually 1. So this is e to the power, the form of e to the power minus at into ut, and ut is nothing but, you all know that it is the unit function. It is the unit function. So the functional value is 1 while t is 0, and then the function drops as because of the term of e to the power minus of at. As we know that a unit function is represented as this. So this is the form of the unit function, unit step function, and this always remains 1 while t is greater than 0. But as here for this function, the value of the unit function is multiplied with an exponentially decaying component of e to the power minus at, and that e to the power minus at diminishes the functional value or the unit value as this. Okay, so here by writing the integral from minus infinity to plus infinity, as because of the unit function always defined at the region when t greater than equals to 0. So beyond that, that is at minus of infinity, the unit step function or the unit function doesn't exist. So this integral limit should be modified, and we can write it as 0 to infinity. And as I have written the integral limit from 0 to infinity, that means within this region from t0 to infinity, in everywhere the unit function remains in its one value, its unit value. So that means ut becomes 1, and the function reduces to e to the power minus of at into 1 into e to the power minus j omega t dt, and we can write it as 0 to infinity e to the power minus a plus j omega then t dt. Is it okay? Have you any doubts? Is it okay? Any doubts whatsoever? I think it's okay. Fine. So now let's move on to get the integral value, and it will be 1 by a plus j omega, so minus 1 here, and then e to the power minus of a plus j omega t, and the limit becomes 0 to infinity. Now putting the value of the upper limit first, that is e to the power minus infinity. Jet explain, Jet, j omega t, I think, Pranav. That is the other form of defining the Fourier transform. That is the other way, that is the other form of defining the Fourier transform. We can define, I think I have repeatedly told you that in both the ways Fourier transformation can be written. So the formula or the definition of Fourier transform, you can write it as f of n equals to integral minus infinity to plus infinity, then f of x e to the power I nx dx, or you can write it as integral minus infinity to plus infinity, minus infinity to plus infinity, and then capital F of x e to the power minus of I nx dx. So earlier in this lecture I have done two problems by using the formula e to the power I nx dx. Now, as I have told you earlier, that I will show you that if the functional form, or rather if the definition changes, or rather if we express it as e to the power minus of I nx dx, nothing can be changed or nothing is changed. You can represent the Fourier transform in either of these two forms. You can multiply the function with e to the power I nx dx, or you can multiply the function with e to the power minus of I nx dx as well. So here in this problem I have shown you that particular part, that where the function is this e to the power minus of at into ut, and then I have multiplied it with e to the power minus of j omega t, that is e to the power minus of I nx. Here the function is given in time domain, so the x becomes t and that becomes I omega t, minus of I omega t, and here here I have written j instead of I. Nothing is changed, and the functional form and the integral form becomes actually, this is the most simplified form, or this is the most regular form. In every time you can find out this particular form as e to the power minus of j omega t dt, as because I have told in my last class also that Fourier transformation is mainly applied to transform a time domain function into its frequency domain function. Okay. So okay, Pranav. So now applying on substituting the values of the upper limit and the lower limit, we can find it as e to the power minus of infinity, and as you know, e to the power minus infinity means 1 by e to the power infinity, and e to the power infinity becomes infinity, so 1 by infinity is 0. So that means e to the power minus of infinity becomes 0, and then comes the lower limit, that is minus of e to the power 0, and that is 1. So minus of 1, that is the value comes from this part, so that becomes the value, the answer is 1 by a plus j omega. So that is the Fourier transform of the function e to the power minus at into ut, and that is 1 by a plus j omega. And as you can see that while the function is given in its time domain, now applying the Fourier transform, we have converted it entirely into its frequency domain. Okay. And I think I must show you uh, how the Fourier spectra looks like after transforming the function. So this is the time domain form of the function, and now when I have reached the frequency domain form, that is g omega equals to 1 by a plus j omega, and if I plot the function, g of omega with omega, g of omega with omega, what we will find? So this is the 0, and if we put omega equals to 0, the value is 1 by a. If the value of omega is 0 is put in here, then the value is 1 by a. Let this value is 1 by a. Now as we move on in either of the two sides of omega, as we move on increasing the value of omega, the function g of omega will be decreased, and that's why the spectra looks like this. So this is actually the Fourier spectra of the function e to the power minus at into ut. This is the Fourier spectra, right? You don't need to draw this Fourier spectra while going through or while attending the problem or by solving the problem. I think as I have came across the Fourier spectra time and again, then I must show you how the spectra looks like. So this is the frequency domain picture or representation of the function in time domain form, which is given here. So this is the time domain functional value or the form, and this is its frequency domain form. Okay. Is it okay? Okay. So let's move on to another important function. And that is known as the rectangular function. That is the rectangular function, or in short, it is written as RECT. That is the short form of rectangle. So this function is also an important function in communication system. So first of all, look at the function here. So this is known as the rectangular function. This is the rectangular function. Say this is the time axis. Let the value is 1. gt, the function is gt. This is 0. This is say tau by 2, and this is minus tau by 2, or you can write it as t by 2 minus t by 2, as you wish. So actually this is known as the get pulse, but as the function is a rectangular form, the function is also known as the rectangular function. Now we have given that the problem is find the Fourier transform of gt that equals to RECT, that is rectangular t by tau, which is actually the form of the function is actually shown in this figure. Okay, so the figure is also given, or you can draw this figure as well. Now, as we know that writing the Fourier transform, that is g of omega equals to minus infinity to plus infinity, the function itself, that is rectangular t by tau, and then e to the power minus of j omega t dt. So this is the definition. Now here from the particular figure or from the graph, we can see that rectangular t by tau equals to 1. The value of the function rectangular t by tau, that is actually 1. The value is 1, while t by tau, that is mod of t is less than tau by 2. Mod of t is less than tau by 2. So this is the functional value. We can define the value from its diagram, that is mod of t is less than tau by 2. When the time value mod of t is less than tau by 2, the functional value is 1. So I have written here as rectangular t by tau equals to 1, while mod tau is less than t by 2, tau by 2, and the value should be 0, and the value is 0 for mod of t greater than tau by 2. So beyond the value of tau by 2 in either sides, the function vanishes. So here we can write this function from the figure itself, the functional value, and putting this functional value in the definition of the Fourier transform, or in the formula given here, we can write that g omega, the integral should be changed, and that value becomes minus tau by 2 to tau by 2. Then the rectangular function value t by tau, that is equals to 1 into e to the power minus of j omega t dt. So the Fourier transform reduces to this way. And now just proceeding towards the integral value, that is, it is 1 by minus of j omega, then e to the power minus of j omega t, where the limit is minus tau by 2 to plus tau by 2. Okay. Now let's put the values, that is e to the power minus of tau by 2, e to the power minus of, so this will be minus 1 by j omega, e to the power minus j omega into tau by 2, minus e to the power plus j omega tau by 2. Okay. E to the power minus of j omega tau by 2 minus e to the power j omega tau by 2. So e to the power j theta minus e to the power minus j theta. If I make this minus sign, product of this minus sign, it will be e to the power j omega tau by 2 minus of e to the power minus j omega tau by 2. So it will be e to the power j theta minus e to the power minus j theta, and that will give us cos theta plus j sin theta minus of cos theta minus, that is, plus of j sin theta. So we have twice j sin theta. Now here theta means omega tau by 2. So we have 2 sine. So that j cancels, and we have 2 sine omega tau by 2 divided by omega. So this is the functional value, or this is the Fourier transformation of the rectangular pulse or rectangular function, rectangular tau t by tau. Is it okay? So I think we have completed the Fourier transformation, and there will be no problem to execute the Laplace as well as the Fourier transformation. So before Puja vacation, I think this is my last class with you, and I have also given the holiday list, or rather the holiday program. So after 20th of October we will meet again. So happy Puja to you all, and goodbye.